Thank you, everyone. Let me continue the program today. Uh, Anyone see the prior I share the screen?
Yeah.
Yes. Uh, Let me introduce the second presenter today. Uh, the second presenter today will be Mr. Milian Grado Gada from Seoul National University of Science and Technology. Hello, Mr. Milian. Let me introduce him through the obstruction. Mr. Milian Guerrero is a member of HUPE. He was born in Ethiopia in 1991. He received his bachelor degree and master degree from Amada Science and Technology University, ASTU, Adama, Ethiopia in 2016 and 2018, respectively. He is currently pursuing a PhD degree in Department of Electrical and Information Engineering at Seoul National University of Science and Technology, Seoul, South Korea. In 2018, he joined the Department of Electrical Power and Control Engineering at ASTU as a lecturer. His research interests include the high efficient power converter technology for EV battery charger and microgrid. Peter Geda was a recipient of the Best Prize Paper Award at APAMC 2024. That means ACC Asia. Welcome, Mr. Million, for coming with us.
Thank you very much for your introduction.
Yes, let me introduce the title of your presentation. The title of the second presentation will be the Reconfigurable single state AC/DC converter for efficient EV charging. And the abstraction of this presentation, I will sort briefly. This presentation introduces a reconfigurable single state AC/DC converter designed for fast EV charger. It offers the higher power transfer efficiency and a wide output voltage range, only while achieve a GPS. The converter incorporates allow rating relays on the transformer secondary size, preset based on the EV battery class to prevent dynamic issue during charging. By optimizing control variables, the design will minimize switching and conduction loss as well as the grid current tested with a prototype power of 8.4 kilowatt and 230 grid input and battery voltage ranging from 150 to 920 voltage. The converter achieve a peak efficiency around 97.15%, enough reliable and efficient charging for both 400 and 800 class EV battery. Mr. Million, are you ready for presentation?
Yes, I will
Yes.
share my
Okay.
presentation slide.
Yes, please share your screen and begin your presentation.
Yeah. Can you cancel your share?
You can try to share your screen.
Okay.
Yes, thank you.
Okay. Here. Okay. Can you see my screen?
Yes, the screen is available now. You can begin your presentation.
Okay, hello everyone. Thank you for coming to my presentation. So I will start my presentation. My topic is high efficiency single stage bidirectional AC-DC converter for fast charger application. So in this presentation, I will present the background of this research, design challenge of the fast charger converter, and the objective of this research. And also I will discuss the prior art for conventional fast chargers. Finally, the proposed converter will be introduced. I will discuss the future operation principle, DBS range, and also the control power control algorithm, experiment result, and finally a conclusion. So as you know, there are two types of EV cars in the market. The first one is a 400 class battery EVs, and the other is 800 class batteries EVs. Even though there is a growing demand of the 800 battery class, still there are wide spread use of the 400 class EVs. So we cannot ignore. So we have to design the fast charger which can cover all the 400 class EVs and 800 class EV battery range. Usually, this is some of the widely used charging profile. You can see this is a vertical line is a battery current. The horizontal line is a battery voltage. So usually fast charger require very wide voltage range, usually from 150 to over 920 volt. So we have to cover all this wide range and also the various type of the charging profile. Here are the reference. I get this charging profile and also the EV type of the various type of EV chargers. So in the EV charger design, we have various design challenge. The first one is increasing power because fast charger require very high power. So the power scaling is a common challenge of the fast charger converter design. The other one is achieving the wide voltage range. As you know, the DAB converter is difficult to achieve the very wide voltage range with a single configuration. So that is the common design challenge of the fast charger. So and also it's very difficult to maintain the high efficiency operation across such a wide voltage range operation. In addition, conventional fast charger use electrolytic capacitor. Therefore, the lifetime of the charger is very crucial. So those are the design challenge of the fast charger. In this work, I said the objective of this work is first design the fast charger which can deliver very high power and also which can achieve the wide voltage range that is suitable for fast charger application while achieving the flat efficiency power conversion. And also we eliminate the electrolytic capacitor which has a shorter lifetime compared with MLCC or non-electrolytic capacitor. So, and also the size and bidirectional operation. This is a common structure of the fast charger converter. 。 fast charger, we have the AC/DC part, which is a rectifier, which simply convert the AC to DC. And also we require very large DC link capacitor here in order to provide the DC input for DC-DC part. And commonly the DC relay is used to diversify the output voltage to supply the wide voltage range required by fast charger. So one of the big limitation of the two-stage converter is the use of the electrolytic capacitor, which has a large size and also the short lifetime. Since the initial cost of the fast charger is very high, so it's very crucial to, it's very sensitive to the cost. The use of this relay is to cover all wide voltage range. However, DC relay is used here, which is very expensive compared with the AC relay. So I can show the operation principle here. They use parallel configuration of the output voltage of this DAB for low battery voltage supply. We can say 400 EV class, and series configuration is used to supply the high battery voltage class. Here are the some of the example. Use fast charger. Usually this is commercialized fast charger we get from ABB and Enercon, and also this is a UV green. Most of them are unidirectional and also two-stage converter. The main drawback of this converter is first, electrolytic capacitor is used, which is very large and also short lifetime. The second one is they require the DC relay, which is expensive. And the other one is since this time the fast chargers are usually designed unidirectional. So in this work, we introduce a single-stage AC/DC converter, which has better performance compared with a two-stage converter. In the single-stage converter, we don't require the bulky E-capacitor. We can just use MLCC, which has a small size and also a longer lifetime operation. Here are the features of single-stage converter. In here, the PFC and the primary side of DC-DC converter are integrated. Therefore, the number of components is reduced. The second one is no need ECAP. And single-stage converter also has a higher efficiency compared with two-stage converter, because we do not require two steps of power conversion. Therefore, the efficiency is higher than two-stage converter. So, however, conventional single-stage converter has some design challenge. The first one is the primary side switch current stress is very high. That is because PFC and DC-DC part of the DC-DC part is integrated, which increase the current stress of the primary side switch. The second one is insufficient output voltage range. The conventional single-stage converters could not cover very wide voltage range that we need for fast charger. Here, I try to analyze the current rating of the conventional single-stage converter. This is a well-known voltage-fed single-stage converter. As you can see, the primary side switch, the current rating is two times the secondary side switch. Therefore, it will be very difficult to increase power, or it will be very difficult to design conventional single-stage converter for high power like 50 kilowatt or higher. The second one is here also the current fed single-stage converter. As you can see, the primary side switch show the higher current stress compared with secondary side. So we have the same issue. The second issue is voltage range. You can see this is a charging profile of the fast charger from 150 volt to 920 output battery voltage range. Here, if we design single stage for 800 battery voltage, we cannot achieve soft switching for low battery voltage. So this is the second main drawback of conventional single stage converter. So in this work, we proposed high power single stage converter structure like this. In here, we can solve the current stress of conventional single stage converter by paralleling the primary side bridge. And also we can solve the narrow voltage range achieved by conventional converters by introducing some reconfigurable relay. This is an AC relay can be used here. So as I said, the future of the proposed, the key feature of the proposed converter is first, we can reduce the primary switch current stress, and also we can achieve very wide voltage range, which is required by fast chargers. Compared with a two-stage, we use the MLC capacitor, which has smaller size and also the longer lifetime. Importantly, the advantage of this relay configuration, we do not change the relay during charging. So here is the overview of the proposed converter. We use 3 modules, module A, B, C. The output current of each module is, as you can see, second order harmonic, only the second order harmonic. When we add these 3 output battery current here, we will get the DC current here, because each input voltage is shifted by 120, so the output current also shifted by 120. When we add these 3 second order harmonic, we can get the DC current. So from this we can say we do not require the large output capacitor for filter, or we do not require the large DC link capacitor. We can use a very small microfarad of the DC link to filter out only switching frequency ripples. So here is a operation principle of the proposed relay configuration. While achieving very wide voltage range from 150 to 920 efficiently, first for 400 EV class, we turn on the relay 2 and relay 3, and relay 1 will be turned off. So here is a configuration. Based on the turn ratio design 1 to 0.5, this configuration is suitable for a low battery voltage class. The other time for 800 battery voltage class, we turn on relay 1 and turn off the other. We can charge the 800 battery class, which is usually from 350 to 920. So in conclusion, while using the same converter, we can efficiently charge 400 battery class and also 800 battery class. This is a DAB equivalent circuit for 400 class, while the secondary side of the transformer is configured in parallel connection. The total DAB inductor is reduced because of the parallel configuration, which helps to boost the power transfer capability. And the equivalent DAB input voltage is equal with each turn ratio 1 times VAB. VAB is a primary high frequency transformer input voltage, and VXY here, which are equal if the turn ratio N1 and N2 are equal. So here is a key modulation strategy. Primary side, we have two bridge. So we have the carrier signal out of phase by 120, and we fix the duty cycle to primary duty cycle to 0.5 to achieve ripple-free grid current. And secondary side, we have one bridge, and we use a duty cycle like a rectified grid current, like this. Here are the high frequency DAB input and output voltage. That means here and here. We use a phase shift between the DAB input voltage and output voltage to control power. In a similar way, we can also analyze the series configuration, which is during 800 battery voltage charging. In here, in order to deal with high battery voltage, we connect the transformer output voltage in series. So the DAB input voltage is the summation of each transformer output voltage, so which is suitable for high battery voltage. Here we have the key modulation waveform for under series configuration. Different from the parallel configuration, we can have the phase shift between BS1 and BS2. We can introduce like this delta, which help to introduce some zero level in the BS. BS is here, like this, which helps to optimize the circulating current and also the zero voltage switching. When we see the current distribution of the proposed converter, since we parallel the primary side bridge, the current stress is reduced. It will be almost like 1-to-1. So we can use a similar switch for primary side and also secondary side. Using the same switch help for reducing the cost for mass production because of the quantity per discount. We analyzed the GBS range under each configuration, 400 class and 800 class. Here we can achieve the soft switching from 150 to 500 at higher power, larger than the 50% here. But light load, still we achieve the hard switching. In a similar way, we can achieve the soft switching for 800 class battery. But still we have the issue of the hard switching at the light load, which is a common issue of the DAB. However, we try to provide some solution in this paper, which is improved light load efficiency modulation for wide mode single stage converter. Maybe we could refer to this one. This technique is not applied here. If we apply this, maybe we can improve the the GPS range at the light load also. So here is the control, closed loop control for the proposed converter. We control the phase shift, as I said before, to control the power. So here we have two loops. Yeah, the first one is the outer loop. Outer loop is only for command input current formation. We can calculate or make the charging profile in here. Based on that, we can generate the command input current, and then we sense the input current. We control the power by the phase shift. So the advantage of this proposed method is we have closed loop solution while changing the duty cycle. We can compensate by the phase shift.
Sorry, Mr. Million and everyone. Because of the limiting time of the team software, so maybe it will close suddenly after 5 minutes later. So when it's turn off, again, rejoin again. Just
Sure.
Please continue. Thank you.
Yes. Yes. So here is a inner loop. We can determine the zeta. I already discussed about this based on this equation. This equation helps to improve the circulating current when we use like this. It depends on the input and output voltage. So here is a 8.4 kilowatt laboratory prototype for our converter. This input. This is the primary side bridge, two bridge we use, and secondary side bridge. Specification is here. The full power is 8.4, input is 230, output voltage is from 150 to 920, and we use a fixed switching frequency 130 kilohertz. So here's the basic waveform for our proposed converter. As you can see, the input voltage VG and IG here it will be divided into two. This current and this current and this current, both sinusoidal. So with this proposed converter, we can divide the power. So we can reduce the primary side switch current stress. The output current is second order harmonic here. But when we when we make the three-phase structure, these harmonics will cancel each other, as I discussed before. So we have the PFC experiment waveform for 800 volt and also under 400 and 800 volt configuration. As you can see, we achieved the good THD with a proposed control, and also we can make some dynamics, and it's very stable operation. We measured the GPS at the worst point, 150, which is the lowest battery voltage. At this point, it's very difficult for secondary side switch to achieve GPS, but with a proposed structure, we can achieve the soft switching with a minimum optimization effort because of the relay configuration. And also at the 480, we can achieve full GPS. We also measured the soft switching for 800 volt EV system charging. Here is the primary side switch 1, the secondary side switch 1. We only show the one GPS for one switch from primary and secondary side, because the other switch also show similar performance. So with proposed control structure, you can see the charging line. The blue one is for 800 class charging line. This is the current. This is a battery voltage. We provide the constant current here. This is a constant current mode. This is a fixed power mode, or we can say CP and CC. Under 800, we follow this charging profile, and we test at the full power. So here, if we don't use relay configuration, the efficiency of the conversion will be very low at low battery voltage, very low. You can see here. But if we use relay configuration, we can achieve high efficiency for 800 class, 400 class, and also 800 class. So we can say with proposed power converter configuration, we can achieve the flat efficiency, almost flat efficiency. This is a loss breakdown of the proposed converter. The dominant power loss is turn-off loss, because we achieved the soft switching. The turn-on losses almost can be eliminated, and conduction loss. These are the dominant switching loss. Here is a power quality. We can measure the THD. Proposed converter has smaller, and the conventional converter, and also we apply the conventional method to conventional converter. This is so. In conclusion, we propose the reconfigurable and high power wide voltage range single stage converter, which can achieve the reduced current stress and also wide voltage range while achieving the flat efficiency under wide voltage range. Proposed relay structure can be applied to any single stage or DC-DC converter. We can apply that to all DAB. So here is the experiment result. We achieved the 97.2 peak efficiency at nominal power, and also importantly we achieved the flat efficiency over wide battery voltage range. Thank you, everybody. This is my presentation. If you have questions, please ask.
Thank you, Mr. Midian, for your interesting presentation. And now it's the time for Q&A part. And from anyone have a question for the presentation? Please, Mr. Thế Tiệp Nguyễn, give him question, please.
Thank you so much for your presentation. My name is Tiệp. I'm from Hanoi University of Science and Technology. Regarding your presentation, I have several questions. First, I understand that the main contribution here is use the reconfigurable relay to make the single state can be work with the battery of the 400 and 800 volts, right?
Yes.
Okay. So how can you control the relays reconfigurable relay? Because the relay cannot be strict instantly, because relay is, in my opinion, relay is very slow compared with the MOSFET. So when you change from the mode 1 to mode 2, the transient must be have a blanking. So in that blanking, in the time changing between mode 1 and mode 2, your converter is work well.
Thank you for your interesting question. Actually, as you said, it's very difficult to change the relay while charging because of the blinking current. We do not change relay while charging. As I say in here, you can see my screen, right?
Yeah.
Yeah. Relay do not change during the charging process.
So
We do not change.
Time limiting is not in my plan. So sorry about that. Okay, just go and continue. We are discussing about the relay, and can you share more about your presentation? Please, please turn on the mic. Mr. Milan, can you turn on your microphone?
Okay. Yeah.
Yeah.
So, your question is the regards to the speed of the relay, and we cannot change the relay while charging. That's true. We do not change the relay during charging in this configuration. The relay based on the preset for 400, we primarily set the relay to the parallel configuration like this, and for 800 EV, we change the configuration like this. This is a preset. We do not change the relay during charging because relay changing time is very slow. That's right.
So how can you? So I have a question about the efficiency. If the relay is not changed during the charging, so why efficiency is improved during the whole range of power if you don't change the relay?
What I want to say is relay will change, but the relay will change in advance before charging process start. Depend on the car. There are two type of car. One is 400 class car. The other is 800 class car. So we set relay in advance before charging process start. We set the relay like this. For 400, we set the relay. We turn on relay 2 and 3 and turn off 1. This is we set relay in advance before charging process start. We do not make the jump from, there is no way to change relay from parallel to series configuration while charging because each car is identified already, some 400 class, the other 800 class. So this is why we change relay, but not during charging process.
Oh, this means you propose the different single state
Yeah.
to improve the strength of the current.
Yes, right. So
And
you see the some car are 400 already, the other car are 800. So in order to deal with both EV car, we use the same converter. We add some relay, and for each type of the car, we only change the relay while using the same converter.
Okay, thank you so much. The second question is, can you move to the slide with the breakdown, loss breakdown?
Okay.
how can you break down the loss?
Actually, we can measure by the PCIP, or we can calculate the other.
This
Yeah.
means this loss is not made by the experiment.
Yes, right. It's analysis. Only by the analysis we can do that.
Okay, so it's very interesting topic because you solve the double life frequency problem in a single state topology by interleaving three phase of input. It's very impressive. So the final question is, how can you control this system in the whole charging process? This means when you have to follow the charging profile.
Yeah.
So how can you do that with
Yes. The first we have to, here is a battery voltage here. Based on battery voltage, you can see the bold one is a nominal battery voltage here. This is here until this is DC mode. Less than 500 is DC mode. Until battery voltage is less than 500. If battery voltage is less than 500, we provide the constant current command, battery current here.
Yes.
In our system, it will be 17 ampere.
Okay.
Yeah. It's 17 ampere we provide until here. After 500 volt, it will be constant power. That means battery current will be like this. This setting is provided by the charging profile. We set like this. This is you can say this is a command for charging system.
Yes.
Yeah.
Okay. Thank you so much.
Thank you.
Yes. Once again, I really on behalf of the feedback webinar team, I really really sorry. I'm really sorry for the the time this interrupt between your presentation, and as the feedback account is not payment, so we just have the 5 minutes left before it's ending. So I'm very sorry about that. Thank you so much for your presentation. I'm very sorry for the inconvenience during your presentation. Sorry about that.
Thank you very much.
Okay, thank you. The question from Mr. Phạm Thế Tiệp. I think the Q&A time is very long. So any question from audience? Please feel free to raise a question to the presenter today. Anyone have a question? Please raise your hand to give him a question.
I have some theory in our lab, EBSC lab, under supervision of Dr. Ding. So we are researching the same topic with the Seoul research. So I know that the Professor Sewan Choi will be come to Vietnam in this year. And do you come to Vietnam with Professor Sewan Choi?
Actually, I want to visit Vietnam. If I get any chance, I will not hesitate. I have a lot of friends from Vietnam.
Yes. Because Dr. Kiều Phúc comes to our lab in 3 days ago, and he's sharing very much about your lab, and I'm very impressive with your lab. And if I have a chance, please give me a chance to working with your lab to sharing about the experience and the publication.
That's
Thank you.
very interesting, and we
Yeah.
can cooperate.
Yep.
That's very good. Yes.
Okay.
Okay. Let me have a question with you, with Dr. Amita Millian.
Good.
Okay. Can you move to the slide 17?
Okay.
17. Okay. Okay. Thank you for your presentation. I think your presentation present a propose a new topology that have a wide output range, right?
Yes.
And I see that actually I see a issue. I see a issue when you see the 900 EV case. The, for example, when you apply for the 800 EV case, the output battery will change from 900, and maybe when the battery is depleted, maybe the output the voltage of battery will very loud. For example, maybe 150. In this case, you cannot control the battery if you don't change the state of relay in the process, because the output only from 350 to 920. And in the case the output battery have a voltage of, for example, 200 or 150, your converter will be limited. So I think it's do you think it's an issue with your proposed converter?
I think the depletion of the battery it can be the it's common issue, because usually the 800 battery voltage require the voltage, the minimum voltage is usually 400, even not 350. But if the battery voltage goes down to 150, I think this configuration may not operate.
Yes.
And also it will be the common issue for the other converter also.
Okay, I think
Maybe the battery management system, it could control it should stop the discharging when the battery is less than some threshold voltage. Threshold voltage is the minimum discharging voltage. I think it should not also go down to 100 volt.
so. So you mean the voltage range of the proposed converter will be from 350 to 920?
Yes, right.
Yes. How do you think about the output range of 800 EV? Do you think the voltage range will be wider that range you mentioned here?
No. It's
No.
within this range. Usually it's from 400 to 850. It's within this range, but this converter we can do more, even more wider range.
I think
920 maybe very big car or bus.
it's better if we have a wider range.
Yes.
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 Is the first question. I have one more question. When you see about the topology in the left side, you use two bridge in the primary side, and each bridge you use interbleed topology, right?
Yes.
So do you have a issue or challenge when you control the system? Because as my experience, when you control an interbleed converter, or when you control two converter in parallel, maybe it will be have a problem of unbalanced issue.
That's right.
So yes,
Yeah.
do you have a
I already
experience
know about
when
that.
you experience with this system?
Yes. Actually, in this converter, we control each bridge independently. We have two current sensor. we have two current sensor for bridge 1 and bridge 2. I can show you from the experiment result here. Can you see this?
Yes.
Yeah, the IG1, IG2, IG1, IG2, we control independently. In order to address the issue of the imbalance, we control each power independently, so we can handle the imbalance issue.
So how about there are 4 inductors in the primary side? How about the unbalanced issue with the inductor?
Yes, that's also the common issue of the current fade totem pole, but we fixed the duty cycle 0.5 in here. And also we have to design the inductor equally. Each inductor should be equal.
Yes, that's mean when you design, you need to care about
yes.
the inductor.
Yes, we have to care the design of the inductor. Then that imbalance issue is there, but in this I did not provide the solution about that. But when I design the inductor equally, there is no issue of imbalance.
Okay, thank you. I have one more question about the conventional DAB converter. There's an issue. It's about the line loss condition. The leading leg and the lagging leg of the bridge will have a different debate condition. So sometimes when debate will be loose when you control the converter in the line loss condition. So I see in your paper, in your presentation, you show that only the debate of switch S2, SP2, and SS2. So how about other switch in your system?
In this converter, leading leg and lagging leg, they have exactly the same performance. But there is no difference in the performance wise. But the upper and the lower switch, GBS performance can be different for positive half cycle and negative half cycle. Only that. Otherwise, the leading and lagging leg has. I didn't see any difference in terms of the GPS.
Okay, thank you. Thank you so much. Anyone have a question with presenter today? No more questions. So I finished my responsible. So please, Mr. Nam, continue the webinar.
Thank you very much.
Okay. Okay. Thank you to two presenters today. Now, the two interesting topic, and we discuss a lot. And I think this audience or speaker can learn a little bit from themselves, and even as a speaker or the audience. So thank you very much to presenter and the audience to join today. So now the time is end. So let's say goodbye and see you in the next webinar.
Thank you.
Okay, see you.
Oh, Mr. Million, can I connect with you to discuss more about technical detail? Yes. Okay, I will connect with you, John. Your research is very impressive, and it's the same with what we are doing in our lab and your company. So please give me the chance to cooperate with you and your research. Yes. Your mic is not. Please turn on the mic.
Okay. We can cooperate, and you can discuss with me anytime. You can just send email, and we can arrange anything.
Yep. Thank you so much.
Thank you. Yes.
Chào mọi người nha, em xin phép em cần.
Chào mọi người, em cảm ơn mọi người. Rất xin lỗi mọi người vì sự cố hôm nay. I'm very sorry for the inconvenience at the time.